So far what we have learned is the we started with the basics of TensorFlow. Then we learned about neural networks. Then we learned about training the neural networks. And afterwards, we learned about CNN, the convolutional neural network. And now we are starting with RNN. All right. So, so before we start, I would like to tell you something that so y- if you pull the new version of repository, yes, I'll share the slides after this. So in yesterday's session, we talked about CNN being applied to MNIST. So if you want to apply the same thing on a newer data, a different data set, I have put an example there. So if you go to deep learning, and here you need to open a terminal, cdml, and say deep learning, and git pull. All right, so you'll get the latest notebook. Done. So you should be in this folder inside ML, inside deep learning. You should be there. All right. So yeah. Now, if you go back to deep learning folder and say go to convolutional neural network, I've added an extra step there. So remember the way we ran our MNIST towards the end. So uh, here we were training the MNIST, right? So first of all, we were creating the whole neural network, the various layers. Then we were loading the data. Then we were loading the data, the MNIST data, right? So instead of this data, we could use something called fashion data, in which given a cloth, given a photo of a cloth, or given a photo of apparel, you have to identify which apparel is it. There are 10 sets of apparels as in the fashion goods. Here there are 10 exactly like MNIST. So the data format is very much like MNIST. So you can try the same neural network on this data and see the accuracy. All right. So without having to do any change, you can just apply the same algorithm on training this. Okay, so you could try this out. So this is basically, as long as your data is exactly in the same format as MNIST, you could apply the same neural network to train and predict. You don't need to change anything. And in case you need to change the format, you might have to just change the number of columns and other things. Yeah. Okay. So as well as the number of inputs here, the height and width might change in case of other data set. But in case of this fashion data set, it'll remain the same. Good. So you could try that out. You could try different number of epochs. So for me, even at say 10, the accuracy was around 92, 91. It went up to 92 once and then came down. All right. This one I had interrupted after 17 iteration. Therefore, okay, I had done another interrupt at 17th iteration because I couldn't wait. I was running number of epochs as 30 that time. That's why. Okay. All right. You could give it a try. This is no longer required afterwards. Uh, this is required. Okay. Yeah. All right. This line is extra, so we could ignore it safely. All right. So you could try it out and great. Now moving ahead to today's session. Did anybody try? All right. You could give it a try later. Let me give you a copy of slides. All right. So should we start with RNN, the recurrent neural network? All right. Hi, Balaji, Binta, Gigi, James, Kamal, Pratik, and Ross. All right. Great. Great. So with CNN, we were able to process any image which has two dimensions and which was to be interpreted visually, like or any data which was two-dimensional and to be interpreted visually. So that kind of data is very well done with CNN, videos and images and similar inputs, right? But when it comes to predicting the future is a consequence of many events. And each event is having an impact on an output in a certain sequence. So basically, predicting the future is what we do all the time, like finishing a friend's sentence. Sentence is nothing but a sequence of words, and anticipating the smell of a coffee at breakfast, and and catching the ball in a field. So all of these are an examples where we are trying to predict the next step based on past few steps, okay, or based on chain of events in past, we are trying to predict the next. All right. So here the most important part is that event A followed by event B and event C and so on. And all of these events in a chain are leading to an output, right? So in this chapter, we are going to cover RNN, networks which can predict future. We are going to apply RNN to various examples such as stock market prices. And unlike all the nets we have discussed so far, RNNs can work on sequences of arbitrary lengths rather than on fixed size inputs. Yes. So yes, you can do time series analysis with with the RNN. RNN can analyze time series data such as stock price, and it tells you when to buy and when to sell. All right. So this it's a quite important chapter and it's quite useful to you, and it is essentially something where which we see all the time, which we see all the time. So in autonomous driving vehicle, RNN can be used to anticipate cars path or cars trajectories, and it can help avoid the incident, right? And RNN can take sentences, documents, as well as audio samples as input and make them extremely useful. Like those who are from the machine learning batch, we were talking about removing the noise from the audio, but we haven't got the actual data yet. What we got from the recording studio is the clean data. So I'm yet to get the raw data. Probably I'll have to buy it. And what we were trying to do is given a audio, we wanted a clean audio, right? So so basically, that those kind of problems can also be very well solved with RNN. And for natural language processing systems such as automated translation, speech to text, or sentiment analysis, even there are many examples of RNN. There is something called there is something called auto there's something called auto reply, a paper from Google in which they have used RNN in order to predict what to suggest next. Okay, like for example, you must have seen in case of Gmail, there are these buttons which suggest what to reply quickly, right? So it suggests like what the next reply should be. Similarly, Google's Allo as well as LinkedIn's messages, all of those have auto reply suggestions. Those can very well be built with RNNs. Okay, so they are all based on Google's paper on auto reply, which is basically using the recurrent neural networks. All right, so using the RNN, we could do a lot. We could do a lot, and we will take a couple of examples. We will start with MNIST, then we'll do stock, and if you have more ideas, you could try those along. All right. So RNN's ability to anticipate also makes them capable of surprising creativity. You can ask them to predict which are the most likely next notes in a melody, and then randomly pick one of these notes and play it. Then ask the net for the next most likely notes and play for it, and repeat the process again and again. So you could train the RNN on a lot of melodies, and then based on the past sequence of the notes that you have played, it can suggest it can suggest the next nodes, and that leads to the creativity, that leads to the creational machine learning models. And here is example of melody. Okay, so let's just uh, hear it. Okay, let's just hear it. And all right, so you could try listening to it. So it sounds like it's composed by it is composed, it's composed by somebody, it's composed by an artist or something, but it is actually generated by an RNN. All right. So so basically using RNN, you can do a lot of magic. A question from Binta is, how about vehicle maintenance by sensor? That definitely can be done. All right. So if you guys have any projects in mind, you think that you should do something, a particular project, feel free to let me know. And we can see where can we get the data from, and or we can see if we can find an open source data set, and we can solve those problems. All right. After we are done with reinforcement learning, we should be ready to solve almost any kind of problems with deep learning and with neural networks. All right. So with RNN, we could do a lot. So in this chapter, we will learn about fundamental concepts in RNN, the main problems that RNNs face, and the solution to these problems, and how to implement RNNs. And finally, we will take a look at architecture of a machine learning translation system. Before these, we are going to walk you through one stock prediction example where we'll have dummy data, and before that, we will try MNIST on RNN. All right, so let's get started. Any questions before we start? No questions? Yes. So projects, yeah. So there are quite a few projects we could do. We already have some of them in pipeline. We're just going to put it up there in the in the LMS. And okay, so let me just mention those in LMS. I think that'll be good enough. Okay, so after this, probably before the next session, we should have the list of more projects. All right. We already have projects planned. It's just that we have not mentioned those inside LMS. We will update that. All right. If you have some projects in mind, feel free to let us know. Also, you could again plan to team up for the projects. Okay. And then execute. But team up hasn't worked in past much, so it'll be better to do it individually and solve those. Okay, so great. Let's move ahead. Now, the most fundamental concept in RNN is the basic recurrent neuron. The recurrent neurons is the basic building block. So up to now, we have mostly looked at feed-forward neural networks. Okay, feed-forward as in whereby the so all of the things that we have learned so far with respect to neural network, it was basically the feed forward, in the sense that we are feeding the data from one side and we're getting the output, where the activations flow only in one direction, right? And from the input layer to the output layer. So RNN looks much like a feed-forward neural network, except it also has connections pointing backwards. So RNNs have this extra component in which the output itself is fed back here. Of course, there is a weight that is multiplied here, and there's a weight that is multiplied here. So this is the input. This is our representation of neuron, and this is the output. And one component of output is being fed back to the input. When we say one component, we are saying that we basically talking about certain multiplication of the weight. So you can think of it that the output itself is being fed back to the neuron. So this one is just composed of one neuron receiving inputs, producing outputs, and sending the output back to itself. All right. So this is the basic building block of the recurrent neural networks. So the say at each time step t, so what happens is, let's say we're feeding the data in the initially, right? When we're feeding the data for the first time, there won't be any feedback and we will be getting the output. Then we'll feed more, second one at the second time. That time, the previous one will be used, will be inputted here, and then we'll get the output. So here, whatever was the in output previously is being put in back. Now, in this diagram, what you see here, as the time is progressing, this is what is happening. At time t, at certain time t, the output from the previous input x at t minus 1 is being fed here. Okay, so output from previous step is being fed here. Same is true with xt minus 1. The input from xt minus 2 is being fed here. All right, so this recurrent neurons receives the inputs xt as well as its own output from previous step yt minus 1. All right. So the important part is that here, this model, this way of representation, the similar one, this one, as with respect to time, is called unrolled model. This is unrolled model. This here, if you look at it from the time perspective, in the initially we'll feed x naught, we'll get some y, and then in the next step we'll be feeding x1 and the previous value, and we will keep on doing it over and over. So the same is represented as unrolled version here. All right. So we can represent this tiny network against the time axis. This is called unrolling the network through the time. So this one is a singular one, singular representation. The same in action is being represented like this. So we can easily create a layer of recurrent neurons. At each time step t, every neuron receives input from both the actual input as well as output from previous one. Here, please note that this time there is it's an extension of the previous one. Okay, this is a hyperparameter that you can control, as in how many neurons do you want in a particular layer. Okay, so if you have more number of neurons, you can learn more things about input and so on. All right. Question from Bintao is, does each neuron receives input? Does each neuron receives itself the input and the previous output as input? Yes. Previous output as input, that's right. All right. So, so what we do is here the important part is just like X is being inputted to all of these neurons, similarly, the previous value of Y will be inputted to all the neurons. Okay, not only the output of the individual, but the overall Y. Okay, so the whole layer of neurons will behave like a single neuron. Internally, it might be built of 10 neurons, 20 neurons, and so on. So the way input is fed to all of the layer in the same way, the overall output will be fed to this layer. Okay, so the whole layer would act like a single neuron. So this is called the layer of recurrent neuron, and this is more practical, and this is what we are going to use instead of a single neuron, because single neuron can't learn much, and because it can have only one weight. Here there are many weights possible, and based on the problem statement, if a problem is complex, we can have many recurrent neurons, and that would help. That would be able to learn complex patterns. All right. So the input vector xt and the output vector from previous step yt minus 1 is being fed at each step to every neuron. Okay. I hope everything is clear so far. All right. Now, how does the calculation happen? How does the calculation happen? You can think of each neuron as just something that multiplies certain weights to the input and gives the output. These weights are basically going to be learned based on the backpropagation. We are going to compute how much error are we getting in actual, and then how much error are we getting in actual here, and how much error we are getting in the output, and then we will propagate the error, and we'll see that how much is the impact by each of the weights. And then we will walk backwards till the point of figuring out which which weight should be tweaked, how much, and so on. So after a point of time, once we have trained it enough, we have tweaked the weights, we have tweaked the weights such that it's giving the results closer to y, the actual output, and then we'll be able to say that our network is trained and we can apply it for predictions. All right. So now let's take a look at the calculation. Don't get intimidated by this. This is actually pretty simple. So each recurrent neuron has two sets of weights. The weights that are applied on the input, and the other for the outputs. Okay. So here, when we are feeding X to this one, or let me just go back one more step. When we are applying this, we have W here, we have W here. These two W's are different. We multiply X with W, and we multiply Y with WY, and then we sum up both of them and add a bias to it and give the output. That's what is represented here. Now, there is one more thing here. It's called phi, which is activation function like ReLU. Okay, so we multiply the xt means the transpose of x. Since xt is a vertical vector, we are making it horizontal by putting t on top of it, by transposing it. So we are multiplying the input with wx, and we are adding it with another term. This is the output of the previous step, and we are multiplying it with wy. Wx and wy are the trainable parameters. In due course of training, these are the weights that we will figure out figure out or tweak such that this output is very close to our actual. All right. So how do we tweak it? Using the backpropagation. All right. So here, once, so we multiplied the input with Wx, we multiplied the previous output with Wy, and we added a bias term. All right. So Wx, Wy, and V are something that we will learn, something that we will tweak and figure out what are those values such that the output is going to be closer. And once we are done with summation, we are applying the activation function such as ReLU. All right. All right. So yeah, I'm just sharing the slides again with all. A question from Binta is how to create weight vectors Wx and Wy. Wx and Wy we will initialize with certain values, right? Certain random values initially, and then we'll see how far are we from actual, and then we will tweak these values. We will keep on tweaking these values in order to achieve the expected output. All right, that's a training phase. Just like we did earlier, trying to figure out the weights based on how much the error is deviating. Okay, so we will backpropagate the error in order to figure out Wx and Wy. All right, so we are going to talk about that today. So here, this one represents the output of a single recurrent neuron, and this is how it looks like. All right, is this equation clear to all? No? Kamal, Bintao, Gigi, James, Pavan, Pratik, Ross, Balaji. All right. All right. So this is the basic equation of a recurrent neuron, whereby these are our weights, as in this is initially we'll keep them random. So we are multiplying the input with the Wx, and we are multiplying the output from the previous step with Wy, adding a bias term to it. Again, bias term is something is a trainable parameter, as in initially we'll just put a random number for it, and later based on our error rate we'll figure out how much to tweak Wx, Wy, and V such that our output is very close to the expected output. So, and then we are applying our ReLU activation function. Why do we apply activation function? So that there is a non-linearity in the overall mechanism. Otherwise, it'll be just linear regression. Question from Binta is, what is the dimension of xt? Xt is a function of our specifications, like how big is our input frame. Okay, how many features are there in input? All right, how many features are there in input? That's the dimension of xt. And all right, is yt also one dimension? Not really. That's what is coming up next. Let me just walk you through that. So yt is the output of all the neurons. So the total number of neurons you have, that is the dimension of the yt. Okay, so basically that is the dimension of yt. Per instance, if you have n number of neurons, then we'll have n values in y. All right. So the same thing. Why do we use linear regression? Sorry, why do we use these linear regression way of representation? Is because instead of here multiplying wx with xt, then multiplying wy with yt, and then adding. So instead of using two different loops, we could just use linear regression, the dot product, right? Dot product by concatenating, by putting x and y as two columns and multiplying it with w. if we had to do this using by ourselves, so what we'll do is generally we'll create X vector, do the dot product with W, then create a Y vector, do the dot product with WY, and then we add. So instead of taking two steps, we could just concatenate these into a single array, and or you can say single vector, and then multiply, do the dot product with W. Okay, so that makes it really easy. That makes it really easy to apply to apply the formula. So in basically in many cases you will learn that when you are not using linear regression way of representation, you would end up with many for loops, and that's one of the reasons why linear regression was so useful in the case where you are multiplying one array with another and so on. Okay. So it's very common here that we are going to multiply one array with another, and we're going to have array of arrays, and so on. So all of this is very simple, very much simplified if we use the linear regression way, not sorry, not linear regression way, linear algebra way. Okay, so the reason why we have the linear algebra way is to make the thing simplified. So question from Minta is xt and yt minus is a vector here? Yes. So we basically put them as two columns, and then we are multiplying with weights. All right. And w is nothing but a vertical vector, whereby wx is one row and wy is another row. So that way, when you multiply this with w, so what is going to happen? This multiplied with this, because whenever we are multiplying the arrays, multiplying the vectors using the dot product, what we do is, let's say, so so if we have, say, this here, this is one value, this is another value, this is another value, this is another value, right? And here, if we have, say, w, right? So this will be multiplied with and let me just put it x here and x here. So this is going to be multiplied with this. Okay, if this was, say, okay, I'm going to put it, say, x1, x2, and this one was w1 and w2. Okay, so what we're going to get is, after we do dot product between them, this is a dot product, a huge dot, and this is going to give us x1 into w1 plus x2 into w2 plus, if there was, let's say, x3 and x4, so it's going to be x3, let's say this is x3 and this is x4, right? When we are moving to multiply this, we are going to again multiply with this. So we are going to get, also this is going to be a vector like this. So we multiply this with this, and this is the second element. It's not summation to it. So it's going to be, second element is going to be x3 w1 plus x2 x4 w2. Okay, this is not plus. Okay, this is not plus. So yeah, all right. So it's going to be a vector whose size is 2 by 1, whose size is 2 by 1. Okay, the size of this one was 2 by 2, and this size of this one was 2 by 1. And whenever we are doing the dot product, these two dimensions, this and this, the column of the first one and row of the second one should be equal, and the output of the output matrix is going to be these two. All right, so 2 by 1. So that's what is happening here also. So we basically simplified this kind of a dot product into a vector, and then we multiplied it with wx, wy. So xt is going to be multiplied with wx, yt minus 1 is going to be multiplied with the wy. All right. So basically, the linear algebra way of representing things makes our life easier, even though we could do it without even the matrix, without even the linear algebra. We could just apply for loop on an array, on arrays, but the life becomes really simple if we use the linear algebra. A question from Vidya is a vector represented as an array in Python or NumPy? Most of these arrays are going to be the array in NumPy, and then internally they are going to be transferred to TensorFlow. All right. So most of it is going to be represented in TensorFlow as a vector. Okay, so YT is a n cross n neurons matrix containing the layers output at the time t for each instance in the mini batch. An important part here to know is that while we are feeding x, the x is while we are feeding x is what? Let me just represent x like this. Okay, so x is going to have the feature 1, feature 2, as well as x is going to have number of records, right? Number of records in each of the features. Okay, so here this is called m and this is called n. So total number of features in x are called n of n inputs, and this is m. So generally, whatever input we have, input has many instances, and input has many features or dimensions. Okay. In case of MNIST, what we do is we make each pixel as the feature, and so on. Okay. So basically, the same way. Let me. Okay. Let me see if I could draw this. So if we have, say, x, which is like this, it has some values, right? x1, 1, x1, 2, x21, and x22. This is our x. It has m number of values and n inputs as number of columns, right? This is what is going to be fed to our neurons, right? And neurons are going to be a layer of neurons are going to be a layer of neurons in which each one is going to have the weight, right? And each one is going to have um, they're going to be n number of neurons. So they're going to be w. So first neuron, second neuron, third neuron, and fourth neuron, right? And all of these are going to be fed to each of them. Okay, going to be fed to each of them. Let me just try to represent it again. So this is W2, this is, and so on. So X1 will be multiplied with W1 first. X2 will be multiplied with, right, W2. Okay, sorry. Let me just try to represent it again. So W is going to be W1, W2, W3, W4 are going to be the total number of neurons, n number of neurons. Okay, and neurons, and each of the weight vector that you see is going to be a vector. Is going to be a vector in the sense that this is going to be a vector which is being multiplied with x1, x11 and as well as x12. So it's going to be so if there are n neurons, there are going to be n columns. Okay, n is number of neurons. Now here each vector, this one is going to be w11, w12, w21, and so on. So this is essentially a single weight. This is essentially a single weight vector, okay, which is being multiplied to our single instance. Okay, if you have n number of neurons, we are going to have n of such weights. Okay, so that's what is explained here, that the outcome of this, when we are doing the dot product between the two, it's going to have how many? So this input matrix is m by number of number of inputs. Okay, this matrix is going to be, each weight is of the size of the input features, right? So this matrix is going to be number of inputs cross number of neurons. Okay, the output of this matrix is going to be a big matrix. The output is going to be this y is going to be of size number of inputs. Oh, sorry. Uh, the input, this is going to be m by n of neurons. Okay, so here the input x, the dimension of input x is the batch size m, meaning number of instances that are being fed in single shot, and the dimensions of x as in how many features are there in each instance. That is the that is the dimension of x, right? The weights, individual weights are going to be a vector itself. So if there are n neurons, there are going to be n columns in it. Okay, so we are representing number of neurons as n of neurons. So this is basically going to have the columns equal to the total number of neurons do we choose. Number of neurons is choosing number of neurons is up to us. Okay, because if we want a complex model, and we will choose more number of neurons. If you want a easier model, then we'll choose less number of neurons. And each of these weights, each of the neuron carries something called a weight. And this weight is basically a vector whose size is equal to the number of features. So W1 get multiplied to this, W21 multiplied to this one, and so on. And we get, this is our Y. This is our Y. Okay. Now the Y's the Y's dimensions are m cross number of neurons. Okay, meaning how many instances were there in each batch by these are number of rows in it, and number of neurons, how many neurons did we choose? So that is y. Now since this y is being fed back to fed back to the input, so there is going to be one more component here which is being multiplied to our y. This y is basically m rows and number of neurons as the columns, right? The same one here. So the weights that are going to be multiplied to it should have the same, should lead to the same dimension as this one. Okay, and so the how many weights are going to be there? The total number of the okay. So can we All right. Sorry for the disruption. I think the network has gone again. All right. I've switched to the different network. Are you able to hear me? All right. Sorry about that. So I'm just trying to explain because the dimensions is something that is little difficult to understand because on the prime facie, if there was only one column in X, only one weight is required, and we are having only one neuron, then we could do it using scalars, right? But since the weight itself, there could be many weights, there could be many neurons, as well as our input could be many dimensional. Therefore, we need to look at it from the vector perspective. Okay, if we were not using this kind of representation, we will be using the for loop. We'll be applying this one for loop on this and so on. So that will be far more complicated. So here, what is the dimension of this one? This is our y, right? The y from the previous step. The dimension of this one is m cross n number of neurons. Okay, number of neurons. While this w, this is wy. Okay, this was wx. Okay, so here the y, or you can say yt minus 1, right? The dimension of t minus 1 is going to be same as what we have right now. So here the number of weights that we are going to choose is the dimension of the weights that are going to be there is equal to number of neurons multiplied across number of inputs. Okay, so I hope the dimensions are clear to you. So n of n as in number of neurons. So this is the one that we chose, and so on. Okay, so let me. I'm hoping that this is clear to all. Should I walk you through over? Let me just walk you through again. So the input that we are going to feed to our network is not going to be a scalar value. It's going to have many columns. It's going to be an array of arrays, or you can think of it like a matrix. It is going to have m instances, which is m rows, right? Because we are going to operate on a mini batch. So it is going to have m instances and n of inputs, n. That's the number of dimensions. This is what is the input. Now we want to basically multiply weights to it, right? So the weights that we will choose must have the same dimension as must have the same number of rows as the number of columns in X, right? So W is something that we choose this way. All right. So the number of rows in this should be equal to this. So whenever we are saying choosing each neuron, the weight should be equal to the size of weight should be the number of weights should be equal to the number of dimensions. Now, since we are going to choose many neurons, therefore there are going to be multiple such weights. So the Wx is going to be of the size n of in cross n of neurons, number of inputs, number of dimensions in inputs by number of neurons. So that's our Wx, right? This is going to give us, if we just were multiplying this and not doing anything else, for the first time when there is no y component coming in, the output that we'll get is m cross n of neurons kind of a matrix, m cross n of neurons. Okay. Now, in the second pass, this yt is going to be multiplied with wy. So the dimension of wy is going to be n of n, the number n of neurons, by n of number of neurons by number of inputs, number of input dimensions. All right. Because when we are going to multiply this with this, we're going to essentially end up with m of number. Sorry, this is going to be wrong. So this is Okay, let me just. So this is going to be a matrix of number of neurons cross number of neurons. Okay, so this is what we are going to describe. So YT, the output is a matrix of m by n of neurons matrix containing the layers output at each time step for each instance in the mini batch, where m is the number of instances in the mini batch and n of neurons is the total number of neurons. Okay, all right. Okay, let's just walk through this one. This will make it very clear. A question from Pratik is m cross n underscore n. N of neurons, as in total number of neurons. N under n of neurons is total number of neurons. Okay. So n of neurons means total number of neurons that we choose. Okay, that's kind of a hyperparameter. Is Wy equals m into n of neurons. Wy equals, okay, Wy is Wy is number of neurons by number of neurons. Okay, the size of Wy is going to be those many. All right, great. So let's just walk over this and then we'll come back. So the outcome is going to be a matrix of m by n neurons, right? The input is a matrix of m by number of inputs, input features basically. Number of input features is n of inputs. So the x is clear, right, to everybody? The x has m rows and number of input features. Those are the columns, right? Wx is a matrix of n of input features by number of neurons. Okay, that is the matrix Wx. Okay, so for each of the input feature, for each of the input feature, we have so many neurons. That's what it means. Okay, so this part. So it has how many columns? Equal to how many rows? How many rows? Equal to the total number of input features. And how many columns? It has the columns equal to the total number of neurons that we choose. Okay, if we just choose one neuron, then we'll have only one column. Not clear? All right. And Wy is a matrix of number of neurons by number of neurons. Okay. The dimension of it's a square matrix where the rows and columns both are equal to the total number of neurons that we have chosen. So the weight matrix Wx and Wy are often concatenated into a single weight matrix of the shape n of inputs plus number of neurons by number of neurons. So essentially, this one, Wx and Wy, the way it is done, we are multiplying this with W and so on. So can I do a better job than this? Okay. All right. Was he able to explain the dimensions? Wy's transpose is going to be equal to Wy? No, no, because uh, even though it's a square matrix, it does not mean that we can the transpose will be equal because the weights would be varying. The transpose is equal for those which are whose values on both the sides of diagonal are equal. Meaning, if we talk about, let's say, this matrix, okay, so if transpose of this one equals, then uh, these two values, this and this value should be equal. Only then this value and this value should be equal. Only then it would be a transpose matrix. Okay, that yeah. Only then the transpose of it will be equal to itself. All right. So it's a square matrix in the sense that it has the total columns and rows equal. All right. So this is what happens. So instead of applying so many for loops and then adding them up, we basically utilizing the dot product in order to compute the y. Okay. Had x been a scalar value and y been had x been a scalar value, we could have just multiplied it by a simple number and by hand, and instead of using a for loop. But if the input has many columns, then we'll have to multiply each of the features with certain weight, and then also feed the output back. All right. So not clear to anybody. All right. So yeah, I can explain. No worries. All right. If you want me, I can explain. If you want me to explain, I can explain that right away. So I hope the dimensions are clear. Is it clear, Balaji, Gigi, James, Kamal, Pavan, Pratik, and Ras? Wonderful. Wonderful. So great. All right, great. So I'll move ahead. In case somebody does not have this clarity, don't worry. It's not going to hurt much. But if you don't have the clarity on dimensions, feel free to ping me, and we can catch up for like an hour or so. I can walk you through this. All right. So I can walk you through the dimensions again in a separate time. All right. So now, since the output of the recurrent since the output of recurrent neuron at time step t is a function of all of the inputs from the previous steps, right? Why all of the inputs from previous step? Because the time t1 is a function of t naught, and time t2 is a function of t1. So recursively, the output at any point of time is a represent is the output of the entire past, so we can call it memory. Each neuron has the memory, or each neuron can be called as memory cell. So a part of neural network that preserves some state across time step is called a memory cell. So the recurrent neural network, each neuron behaves like a memory cell. So in general, a cell's state at time t is denoted by HD, is a function of some inputs at that time step, and its state at previous time step was so so okay, let me rephrase. So in general, a cell's state at any time t is denoted by ht, and it is a function of some inputs at that time step plus plus the its state from the previous step. So this is what we just studied. So ht, the output, is a function of ht minus 1 and xt. Its output at the time step t is denoted by yt, is also the function of previous state and current inputs. All right, so like this. So we can say that, okay, so sometimes instead of feeding the entire y, we feed part of it. Okay, so so ht is essentially the output of this one here. Okay, so instead of feeding in terms of representation, the output of this is called y, and the one that we are feeding it back is called h. Okay, in case of basic cells we have discussed so far, the output is simply equal to the state, but in more complex cells this is not always the case. In some cases h could be different from y. Okay, now this was simply recursion, or you can say recurrent network. Now, the a recurrent neural network can behave like a sequence-to-sequence network, meaning an RNN can simultaneously take sequence of inputs and produce sequence of outputs, right? So we are feeding inputs, we are getting outputs, right? So this is basically called a sequence-to-sequence inputs, sequence-to-sequence network. Sometimes that's not the case, as we'll study further. This type of network is useful for predicting time series, such as stock price, and we feed its price over n days, and it must output the prices shifted by 1 day into the future, from n minus 1 days ago to tomorrow. Okay, so basically, this is how the sequence to sequence network looks like. So we feed its price over the last n days, and it must output the prices shifted by 1 day into the future. All right. Now, um, this is called sequence to sequence. Now, sometimes we don't want the output right away. We keep on feeding the input sequence, and after a while, we would like to observe the output. This is called sequence to vector. So in case of sequence to vector, we do not extract the output. We keep on ignoring the output. And after a while only, once we have finished feeding the whole sentence or finished feeding the whole set of records, only then we observe the output, because we know that whatever is the result that is coming here is kind of useless. Okay, we're going to only finish the entire sentence, then we are going to observe this. So this is, so say for example, let's say we are trying to do the sentiment analysis of movie review. So we will be feeding set of words to it, right? So we fed the first word, second word, third word, fourth word, and so on. And only when we have finished feeding the entire sentence or entire review, only then we will observe the outcome, because before that, if we try to observe, then the output will be wrong. So it's like saying that, um, let me first complete, then I'll hear your response. It's like this. So we finish the input, and then we observe the output. Okay, so this is for those cases where sequence to vector is needed. And because last couple of words in the input could actually change the entire meaning. All right. Therefore, sometimes we choose to ignore the outputs of the network until a specified time. Such networks are called sequence to vector networks. All right. A question from Bintao is that how about the accuracy of its predicting a stock price so far? All right. So I have not actually tried. And most likely it's going to be a function of how good the data you have and how much data can you feed. But it can be experimented with. All right, so there we go. And now there's something called vector to sequence. We could feed the network a single input at the first step and zeros for the other steps and let it output a sequence. For example, an input could be an image and the output could be caption for the image. So if you combine these sequence to vector and vector to sequence kind of networks, we basically call it encoder decoder pattern. In this network, we have sequence to vector called encoder, followed by vector to sequence network called decoder. So first, it's like chat. First, we input the data, then we observe the output, then we again input, then we observe the output. Or if we can see the same phenomena in any translation that we input our sentence, then we observe the output, then we again input and we observe the output. So basically, this is encoder decoder kind of a network which we could build out of recurrent network. Okay, a question from Yadao: why cannot the softmax function be used here to cover ignored output? Okay, so why cannot the softmax? So here the network is giving us results and we purposefully want to ignore them, that because we know that we are not yet finished. Okay, so the softmax function is used when we want to push a value to within a certain range. Okay, only then we apply the softmax function. All right, so the softmax function will be used as part of the okay. mm, all right, so I'll have to think over how can softmax be used here, but here we are purposefully ignoring the output or we're purposefully feeding the zero. So this is essentially our inputs and outputs, and it's as per this is what we want as the design. All right. So this can be encoder decoder kind of pattern. Encoder decoder kind of pattern can be used for translating a sentence from one language to another. We feed the network a sentence in one language, the encoder learns it, and then the sentence mm, it basically learns it by converting it into vector representation, and then decoder recodes the vector into the sentence in another language. So this two-step model works much better than trying to translate on the fly with a single sequence to sequence RNN. with a single sequence to sequence RNN, since the last word of the sentence can affect the first words of the translation, right? So this kind of pattern is what is used in, say, translation, in chat, in suggesting the auto replies, and because even the last words in the input would completely entirely change the meaning of the whole sentence. Therefore, it doesn't make sense to keep the it doesn't make sense to note the output before we have finished the entire sentence. So we first fed the first word as input, second word, third word, fourth word, and fifth word. And then once the entire sentence is finished, then we are observing what is the response. Before that, of course, our network will be giving the output on even the first word and second word and third word and so on. But we want to just observe after we have finished feeding the sentence. All right. So so we need to wait until we know the entire sentence. All right. So let's build a recurrent neural network in TensorFlow. All right. So we're going to do a very simple exercise of building an RNN in TensorFlow. All right. So let's implement a very simple RNN model without using any of the TensorFlow's inbuilt functions. And this will help us understand what goes under the hood. So to create RNN composed of a layer of 5 recurrent neurons using the 10H activation function, and assume that RNN runs over only 2 time steps and takes input vectors of size 3 at each time step. All right, let's take a look. So here we have how many inputs? We have total number of inputs as 3, meaning these are the, okay. So number of inputs as in the columns in our input dimension, the columns, the num input features are 3 in our data, and we are choosing 5. So X naught is a placeholder. X naught is a placeholder in terms of TensorFlow's terms. The placeholder is something that we can feed the input later while running it. So X naught is the first input that we are going to feed. X1 is the second input that we are going to feed. And X naught is going to be many instances. This is none is for many instances, and its columns are going to be number of inputs. Similarly, for x1, it's exactly same as x naught. Okay. Then we are defining the weights. Weights are nothing but random numbers right now. These are random numbers, random based on the normalization or statistical normalization way instead of linear way. So we're defining wx, which is a variable, meaning it's going to be trained, it's going to be tweaked. This is going to be fed as in while running, we will be feeding this as input. And the shape of wx is number of rows are equal to the number of inputs. Okay. And number of columns of wx is how many neurons do we want, right? Wy is having a shape of number of neurons by number of neurons. Okay. Then we are defining a bias. We're defining a bias which is equal to which has 2 dimensions. The first one, it has only 1 column, 1 row, and number of neurons, those many columns. So this bias is added per neuron. Okay. Now, so we have defined wx, wy, and b. The initial value of bias is 0, and then we are saying y naught equals. So for the first time, y naught is equal to the activation function of matrix multiplication of x naught and wx. X naught dot wx is what this means. So we are saying multiply x naught with wx and add b, because for the first time when we are computing, there is no y to be fed back. But in the second one, when we are computing the output for the second one, y1, we're going to have the new input, x1 multiplied by wx plus b, and then we are, okay, so then we are multiplying y naught with wy, and then we are summing all of it. Question is, why is wx created with random normal? Here we are basically filling these values with random numbers, while b we are keeping at 0 in the beginning. So initially, the values of w are random numbers, and later on when we train it, we will fill it with, we'll try to improve these values based on the backpropagation. All right. So the network looks like a two-layer feed-forward neural network with two differences. The same weight and bias systems are shared by both the layers. Okay. So since in the next, so it looks like normal, as if we have two neurons in the two layers, one going to another and so on. The only difference is, since it's the same neuron, therefore the weights and bias terms are shared by both, right? So so we can look at it as if it's two layer and two layer of network. The only difference is the bias term and weights are same. All right. So let's input the data to it. A question from Pratik is, so this means that the output of each neuron, this means that output of each neuron t minus 1 is fed into each neuron of time t. That's correct. That's correct. All right. So whatever is the output of y0 is being fed here. You can see that's the way it is. Y2 will be feeding y1 instead of y0. Okay. Now let's try to run it. So we have x0 and x values of x0 and x1. So let's say we have two batches, x0 and x1. This batch is being fed at time 0. This one is being fed at time 1. These are in each of the mini batches. We have instances 0, 1, 2, and 3. So first at time 0 to t0, we are going to feed this mini batch. Then at time 1, we're going to feed this one. Okay. So x0 equals this and x1 equals this. It has m number of instances. Okay. So each of these are 4 in numbers. All right. So we are going to feed this and then we are going to observe the value. To run the model, we need to feed the inputs. Mini batch contains 4 instances, each with input sequence composed of exactly 2 inputs. Okay. Each with an input sequence. This is 4, right? Okay. Yeah. So we basically have 2 input at time t, two at t0 and t1. So this is x0 and x1. All right. A question from Binta is y2 will be correct. That's right. That's right. All right. So this mini batch contains 4 inputs with having three features. These are 3 features, 1, 2, and 3. These are 3 features, and it contains basically the total number of batches are 2. Okay, this is yeah, and at the end, the value of y naught and y1, while we are running it, take a look at this. So while we are running it, we are saying session.run y naught followed by y1, meaning both will be executed. And while this gets executed, y1 will be utilizing the value of y naught. Okay. If you remember the discussion we had during TensorFlow, that if we are calling session.run on two dependent variables, y1 depending on y naught here, therefore first y naught will be computed and then y1 will be computed, and then we will be feeding the we'll be feeding the here we are feeding the entire batch, the x naught and x1. So x naught and x1, the values are given here, and based on x naught, based on x naught, y naught is computed, and based on x1 and y naught, y1 will be computed. All right. So this is a extremely simple neural network that we are trying to build. It's essentially useless other than for the this is only for the demonstration purposes. Okay, there's no other use of it. All right, so let's get started. So please open the recurrent neural network. Have you pulled the latest repository? If you have pulled the latest repository in the files, you will see recurrent neural network. Okay, so you will get this notebook, and okay, so we are importing TensorFlow. All right, we're importing TensorFlow, and at this point, okay, now these are general utilities that we always create, like save figure, reset graph, and so on. Okay, now we are here. We are basically creating the input, like the something that will be fed, then initializing weights with random numbers, and initializing the bias with zeros, and then we are computing y0, y1, and so on. So till now, we haven't done much. We have just defined the initializer. Now we are defining the two arrays, okay? And after that, we are we are running it you in the session, okay? And once we have done running it, we will be able to print the values of y naught and values of y1. So for each of x naught and x1, it has given us the result. All right. So the outputs are going to be total number of equal to total number of instances in each batch. Y naught will have 4 answers for 4 rows. Similarly, Y1 will have 4 rows, and the total number of neurons that we chose will be the columns in it, right? M cross N of neurons. Okay, so this is what is Y naught and Y1. Yes? Did it run for you? Did you try? All right, great, great. Only James tried? All right. So please keep in mind that make yourself comfortable with TensorFlow, because it takes some time to get used to TensorFlow. All right. Try tweaking the values. Try facing the errors that you will face when we are running in TensorFlow. Say, for example, the common intuition would be that let me just take a look at say here y naught and y1, right? Let's say we want to take a look at what's there in y naught, right? You'll see, oh, it's just a tensor. It doesn't have anything. Okay, it doesn't have anything much. So that's when we realize that, okay, we may have to run the session. So run it in the session, or we might have to call it like t y naught dot eval, and then we'll be able to get the results. Okay, so keep this in mind that getting used to TensorFlow takes a bit of time because we have got too used to our numerical computation, that is the usual programming, while this is more like algebraic computation where we define everything in terms of x and y and then in terms of variable, and then we feed the values from outside. Okay, so that's what is different about TensorFlow. Okay, so make yourself comfortable, try experimenting with it. The more you experiment, the more comfortable you will be. All right, so now we are going to try using something called static RNN for building the neural network, and then we'll use dynamic RNN, and afterwards we'll talk about the backpropagation, and then we will do a MNIST example. Great. So far, what we have done is we have just hand coded the RNN with only 2 steps. Okay, only 2 steps. So let's go one step ahead and try to create RNN using the static RNN function. So let's look at how to create the same model using TensorFlow's RNN operations. The static RNN function creates an unrolled RNN network by chaining the cells. The code below creates exactly same model as what we have done previously using the something called basic RNN cell. Basic RNN cell takes an argument called how many number of neurons do you want, and this cell is we're going to make a RNN out of it. So this is one basic cell which has number of neurons, which does all the it essentially internally does the matrix multiplication and has the weights in it. Now, okay, so at this point, when we are creating a static RNN, we're feeding the here we are feeding the basic cell, whatever we created previously, and the inputs x0 and x1 and this. Now here, please note that x0 and x1, it's an array that we are feeding to it. This is an array that we are feeding. So if we are having many of such values, we might have to feed all those values as an array. All right. And we get the output sequence here. So we define our placeholder as usual. Then using tf.contrib.rnn.basic cell, we created the basic cell, and then we created the static RNN using this function. All right. So y0 and y1 are our output sequences. All right. Okay. So you can think of this as it's like a factory that creates copies of cell to build the unrolled RNN. So you will be using this for creating more and more cells, and that will be used for creating the feedback. Every time a new input comes, a new cell will happen, and the output of the previous cell will be fed to the next one. That will happen this one. So static RNN, giving it the cell factory and the input tensors and telling it the data type of the inputs. This is used for creating the initial state matrix, which by default is full of zeros. Okay, so the static RNN returns you 2 objects. One is the entire sequence of output objects, and and the final state. So entire sequence of outputs as well as the final state. These are the two things you will get. Okay, so these are the two outputs that you will get as a result. So the first is a Python list containing the output tensors of each time step. And the second is a tensor containing the final states of the network. In this case, y1 is going to be equal to the final states. When we use basic cells, then the final state is equal to the last output. Okay, so output sequence is the output of x0, x1, that is y0, y1, and the states are basically equal to the last output. So let's take a look at the actual code. Okay, so here we are saying number of inputs is 3, number of neurons is 5, and here we are creating a placeholder x0 and x1. That's the usual way of declaring something that can be fed from outside. And then we are defining the basic cell. Then we are creating the static RNN. Okay, then we are initializing all the variables, and afterwards we are running it. We are creating the input data, and then we are creating the session. And with this session, we are running it. First, we are running the initializer, and then we are running, in this session, we are running these two, y0, y1, and states. Okay, this is just to see. The only difference I have done is I have put states also, just to understand what is there in the states. Okay, so we are saying session.run y0, y1, and states. Okay, and we are feeding this dictionary. Basically, we are feeding a dictionary containing x0 as this one, x1 as this one. All right, so you can see that it has done the computation. And if we check the output of states, so you can see this is actually same as y1. Okay, so states represents the outcome of the sequence of inputs that you have given to it. Question from Vidya is, could we use output sequence instead of y0, y1 here? Yes, you can. Okay, so instead of this, you could actually say something like this. We'll just put underscore say v, and here we could take a look. So this is essentially the array of arrays. Okay, so this is same as y0, right? And this is same as y1. This is same as y1. All right. Okay, so yes, we could use that. Great. So we were able to do the y0, y1 computation using TensorFlow, but it is extremely basic, extremely basic. And if you want to check whether y1 and statesval are equal, you could just say np all. And so this way you can compare two vectors if they are equal or not. Now we can run this particular snippet of code and can load the graph here. It might take a bit of time to load. So you can see here, this is our main graph. This is our main graph. Okay, so there are placeholders and placeholder one. We basically feeding these placeholders to it, and this is our RNN as defined above. Where did we define it? If you go up, all right, yeah, here. So this is where we have defined it. Let's go down. Okay, so it has basic RNN cell and it has all the other parts. All right. So we can take a look at the graph. Right now it doesn't make sense because we have only simple, very simple um, inputs. Okay. So in the previous example, there were 50. If in this example looks okay, but if we had like 50 X naughts, the inputs array of 50, what will happen is it will not be very convenient to define. There will be 50 placeholders, X0, X1, X2, X3, and so on. And there will be 50 output tensors. Moreover, at execution, we would have to feed each of the 50 placeholders and manipulate the 50 outputs. So we could actually make it a little better, make it more dynamic than statically defining the variables. So here we are defining X as a three-dimensional vector. Number of instances is the first dimension. Number of steps is second. Instead of saying x0, x1, we are making that as part of the dimension, part of the vector itself, and the number of input features. So these are the three dimensions of capital X. And then we are saying X sequence equals TF dot unstack and transpose. Now this next part requires a little bit more of more detailing. So let me walk you through what does it mean by transpose and what does it mean by unstack. All right, let's take a look. So imagine that we have defined a three-dimensional vector like this. This is a three-dimensional vector. Why? Because you can see there are three square brackets. So this is one containing each row. Okay. So it has three rows. It has say 4 rows. Okay, these are the 4 rows, and each row has two time values. This one is for T0. This is for T1, and there are 4 instances in total. And here each one is having three input features. Okay, there are total of 3 input features in X. So if we say TF dot transpose, if we say TF dot transpose, what we are saying is we are rearranging the dimensions. We are saying take the first column to the second place. 0 means the first column, 1 means second column, and 2 remains exactly where it was. Okay, 2 remains exactly where it was. So basically, when we want to swap the dimensions, then we use pum. So this basically swaps the dimensions. So the 0th dimension will be the one which was the first dimension. All right. So that we have put it into V. Also, you can convert a 3D array or NP array into a normal array by using unstack. Okay, you can convert a three-dimensional vector into an array of two-dimensional vectors using unstack. Okay, so let's take a look. So V, when we say transpose, so we define V, then we define VV, and then using the session, we run these. Okay, so when we run s dot run V, this is the output. This is the result. Okay, this is the result. So since we have swapped the dimensions, now we basically have this, and this together. Okay, so we have picked for each timestamp, we have brought all the records for each timestamp together. That's what we have done. We have not touched the third dimension, which was, what was that? The third dimension was number of input features. We are leaving the input features as such. We've just swapped the second dimension and first dimension. Okay, that's what it means by transpose. Okay, this is important because you're going to see such kind of code again, and that might confuse you a bit. Now, when we are saying session.run and we are passing the second value, we can see that it has unstacked it. What does it mean by unstacking? This is what? This has two elements. One is this element, second is this element, right? This has two elements. So we have basically, after swapping, this is what we get. So there are two rows. Now, when we say unstack, it's going to convert them into an array of two vectors. So this was a three-dimensional vector. Now it has broken it down into array having two elements. Each element is two-dimensional vector. All right. So transpose swaps the dimensions, while unstack breaks a big matrix into arrays. All right. Why we have done this? Because because in the input which we are going to feed, we need to give it an array of two-dimensional matrix like x0, x1, x2. That's why we had to transpose and unstack. All right. Is this clear? What does it mean by transpose and unstack? Ross, Pratik, Pavan, Kamal, James, Gigi, and Binta, Balaji, Shahrukh. Yes. Perm equals 102 means permuted, as in, let's say here we want to swap the dimensions. We want to swap the dimensions such that this becomes the 0th dimension, right? So we could say, let's say equals, I'm just putting some new values, okay? So if you want to say transpose this into such that the last dimension becomes the first dimension, let's say this, okay? The middle one remains as such. Okay, so let's take a look. Now, you see? All right. So this one became the first dimension, as in when we are accessing these as index, this is what is going to be. So 0, 1, 2. So 0, 1, 2. That's how it has broken it down. And right, and so on. So basically, we change the dimensions instead of addressing the instances first. We made it address the steps first, and here we made it. So how should I say? Okay, how can I give you a better example? Okay, so let's say x1 is this, okay, and uh, x1 is this, and x2 is this, okay. And let me just comment it out for time being. All right. So here, if you take a look at x, x looks like, okay, I'll just compute it. Okay. So if you take a look at xx, it looks like this, right? So excess is 0, or let's say 1 means this, right? And let's say in the second instance, in the second instance, we want to take a look at say 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 0th value, okay, and say these are number of instances, and we're looking at the timestamp t equals 0, okay. So this is m equals 1, okay, mth, all right, instance, instance equals 1, and time equals 0, and let's say feature equals 2, okay, feature equals 2, okay, sorry. So this is 5, all right. When we have swapped, the inputs, like we have first done the permutation, v is x1. So if you take a look at x1, what has happened is dimensions are swapped. Okay. Now 0 means this is the 0th timestamp. Okay. And if you want to access the first instance of it, we'll say right. So yeah, we'll say this 1, okay, and 2. Okay. Now, the most important part to notice is that when we have swapped these dimensions 1 and 0, the same indexing swap is going to happen here. Same indexing swap is going to happen here. All right. To access the same value which you used 1 and 0 earlier, now you're using 0 and 1. Okay. Like the way we swap I and j in two-dimensional matrix, similarly, we have swapped we have swapped the first two columns, first two dimensions using the transpose. All right. So I and j became j and I. That's what it means by transpose. And in this one, the last one, where we have defined, say, x2, okay. X2 is, if you take a look at x2, x2 looks like this. And since we have swapped the last one in this way, we'll have to say 2, the middle one will remain 1. And so what was this was the value, right? So 2, 0, and 1. Okay. So you can see, since we have swapped the last two, first and last, in the same way, the addressing scheme has also swapped. Okay. So 2, 1, 0, 2 became 0, 2, 2, 0, 1. All the values, the way we were accessing them, if we were accessing them with, if this was say, let me conclude here. So if this was our ijk, this was I, J, K. This was the usual permutation, the actual. Okay. And in case of, say, x1, okay, x1, the way we are going to access the same thing as J and I and K. So these elements are equal. All right. So K, J, okay. So these permutation, this will help you. Here, It takes a bit of time to get used to more than two dimensions. Okay, so this one is the default one, and here in the second one, the 0th column went to the first place and first column came here. Therefore, we have swapped the first two columns. Here, we have swapped the last and first columns, while the middle one remains same, and same has indexing changed. Yes, perm represents permutation. All right. So whatever value you put for I and j, okay. So let's say I equals 1, j equals 2, and k equals 2. So you can see here, if I just say print, all right. So whatever value, you can see that the values are swapped. That's what it means by. Okay. All right. So yes. So since our data is such that the first dimension was, since our data is such that our first dimension was number of instances, we wanted to unstack the instance, unstack the time step separately. Therefore, we first made the time step as the first dimension, and then we unstack it. Unstack means separating them into separate arrays. Okay, that's what it means by unstack. All right. So converting this into such that this is our T naught, okay, and this is our T1, or this is our X naught, into such that this is our X naught and this is our X1. Okay, that's what is happening as part of what we're just doing. Okay. All right. So this is T1, this is T naught, and so on. So these are juggling with the dimensions. All right. So this is what's happening here. We are converting X into X naught, X1, X2, X3 kind of an array. And let me just define number of inputs. Okay. And initialize it. And then we just run it. Now, once we run it, we get the output. All right. So that was the reason behind using the unstack. Okay, so this is a bit better method because here, instead of hard coding X0, X1, X2, we were able to dynamically feed the data and get the results. Okay, now, all right. Great. So should we move ahead? So we were able to basically run the static RNN, and we were able to feed the dynamic list of data. All right. The only difference is that we were using the unstack and transpose, and also here we are not doing it very efficiently. That we'll learn very soon. All right. Now we can run the network by feeding it a single tensor, And this is how our mini max look like. Then we get the get cell output well tensor for all the inputs, all the timestamps, and all the neurons. Okay. Okay. So this is what we do. Now, the previous approach that we just used. So why we are going in stepwise so that we understand what's going on underneath. Otherwise, everything would look like magic, and you will tend to memorize. Okay, tend to memorize as in you will overfit everything. All right. So the previous approach is still builds a graph containing one cell per time step. Right. There were 50 time steps. The graph would look ugly and it'll look complex. So if there were 50 time steps, the graph will become basically complex, and it's equal to writing this y naught equals f of 0 x naught and so on. With such a large graph, since it must store all the tensor values in the forward pass so that it can compute them using the gradients during reverse pass, we may get out of memory errors. Because GPU, though it's very fast, what is GPU? GPU is basically many processors bunched together for graphics processing. But GPU cards generally don't have that big a memory. They buying a 8 GB GPU is a costly affair even today. All right. So during backpropagation, it will store entire tensors, and hence it'll lead to the out of memory. This is where dynamic RNN comes into play. So dynamic RNN function is like a while loop, while the previous one was actually like typing the code. So it uses a while loop operation to run over the cell the appropriate number of times. We can set swap underscore memory equals true if we want to swap the GPU's memory to the CPU's memory. And in order is so that during backpropagation, the memory errors do not occur. It also accepts a single tensor for all the inputs at every time step. And it also accepts a single tensor for all the inputs at every step. And it outputs a single tensor of all the outputs at every step. There is no need to stack, unstack, and transpose. So we could use dynamic RNN very simply. We basically are saying here, the basic cell and everything remains as such. We just are using here a term called dynamic RNN, and we are calling this function called dynamic RNN, and it's creating the dynamic recurrent neural network. So we're getting the outputs and states. So let's take a look at the notebook. All right. So here is the we are initializing. So total number of steps we are going to have is 2. Total number of input features is 3, and total number of neurons is 5. And here we're defining the placeholder as usual, and then we are creating the basic cell. Basic cell is something that we will create all the time, and then we are defining our dynamic. Then we are calling the dynamic RN function. So it essentially is a for loop under which it's going to call this. Then we are initializing all the variables. And afterwards, we are creating our array. Okay. And then we are running it. After running it, we'll get all the outputs, and we can take a look at the graph. A question is, why use n underscore steps equals 2? We can use any number of steps as we want, provided we have the data. Let's say we were using more than 2 steps, say we were using 3 steps, then we will have to have, say, more columns here. All right. So we'll have to have more columns here then. Okay, let me see if it works. So we have put more time values now. Okay, so we could have more. The more number of steps we have, the more data we'll have to feed, right? At every step, this is what we are going to feed. Okay. So this is how it looks like. The RNN is doing the internal transpose and all. Okay, cool. So this way we could create a dynamic RNN. So there is a while loop here over basic RNN. All right, rest is everything internal. Great. So, all right. So that was how we will create the dynamic RNN. We are not yet training it. We're just creating the network right now. All right, we're going to train it exactly the way we trained other neural network by creating the optimizer and so on. We'll create a loss function. We'll create the loss function, then we'll create an optimizer, and then we'll run the optimizer and optimizer.minimize, and that's how we're going to train it. All right, so now note that during backpropagation, the while loop operation does the appropriate magic. It stores the tensor values for each iteration. It stores the tensor values for each iteration during the forward pass so that it can use them to compute the gradients during the back pass, the reverse pass. Now, so far what we have used is only fixed sized input sequences. So far, we have only used the fixed sized input sequences. What if the input sequence have variable lengths like sentences, right? In this case, in this case, we should set the sequence length parameter. When calling the dynamic RNN function, we would be setting the sequence length parameter, and it must be a one-dimension tensor indicating the length of the input sequence for each. Okay, so if we have varying number of sequences in the input, right now we have all the instances or all the batches that we are feeding have equal number of steps, right? In some of the cases, we may not have all the steps. Right now, we have total number of steps as 2, and every instance was having 2 values. What if some of these are missing, or some of these are missing, or some of these are not really possible because, say, every sentence could be having different length, right? So that way we are going to use the so so we're going to use the dynamic RNN with the sequence length. Okay, so suppose the second input sequence contains only one input instead of two, right? Instead of two, let's say we have only one input, then we must put zeros in it in order to fit the input tensor X. And then while feeding, while feeding, we need to feed values for both the placeholder X and the sequence length. Okay, so while feeding, we're going to feed the sequence length for every batch. Okay, and now the RNN outputs zero vectors for every time step past the input sequence length. Look at this second instance is output for the second timestamp. So here what we are trying to demonstrate is that in case our input sequence have varying lengths, we just need to compute the varying lengths and then pass that varying length and pass that length for each of the instance each of the instance, the number of total sequences we are feeding it every step, every time we are feeding it, so that it knows not to misinterpret the values. Okay, all right. So moreover, the states tensor contains the final state of each cell excluding the zero vector. Okay. All right. So since in case of RNN, we are going to feed in the sequences into the system, therefore we must make sure that we must be able to handle varying input sizes. All right. Now let's take a look at the here. Let's say we have these inputs. This is standard one that we have defined earlier also. Then we are defining our dynamic RNN. And here the difference is that we are passing the sequence length along with it. Okay, so dynamic RNN, we are passing the sequence length, and sequence length is something that we are computing here. We are basically creating a placeholder for sequence length. Okay, and then while we are feeding here, feeding this X batch, we are going to give the length of each batch. Okay, like here we have explicitly mentioned that first one is of two length, second one is one length, third one is two length, and fourth one is two length, and so on. So this way we could feed the batch. Okay, all right. So here let me just again run it from the beginning. Okay, so it has done the computation, and you can notice that this is 0, and the states overall are basically this particular output of the sequence has been completely skipped. Okay, this is completely skipped. We have the second, because there are two time steps, right? So out of every instance, the last one is what is retained as states values. Okay, so instead of giving out 5 results for one for each instance, it has 5 instances, right? Just a second. Yeah. All right. Okay. No, it has number of inputs as 3. No, it has a number of inputs as 4. Okay. So here, total number of 4 instances. Okay. And features are 3. All right. So out of all the, okay. So yes. So the time the states was 0, it has picked the previous value x1, x0 instead of picking x1, while in all other cases it has picked x1. Okay. So the states means the states value is always the final outcome. All right. In case this a particular state's final outcome is 0, or it is skipped, the previous value is retained. Because there was no output, it was not fed a second time, therefore we get the previous value. Okay. A question from Binta is, how about sequence this? Okay, sequence as in, yeah, here. Let's say here while feeding it. Okay, so since the here, what is it that we are saying? We are saying the length of this input. So there is, it can be either 1 or 2, right? Because there are only 2 steps. So if we say 1 here and we're passing it here this way, so you can see the moment we say specified that the length of the first input is going to be G1, it has ignored the second input. All right, it has ignored the second input. All right. Is that what you wanted to do? We can't specify 4 because 4 means there should be 4 such steps. Right now we have 1, 2. There are 4 instances, but there are only 2 steps. So here we have to specify the length inside each instance, length of total number of steps. Okay. So great. Now that was okay. This is all right. Now where did it go? All right, so let's get started with training the neural network. All right, now moving ahead. Yes, yeah, I think you can choose 0. I can try 0. Let me try 0. What happens in this case? You can see both the outputs are 0 because it's thinking that no input was passed. All right, great. All right, so this was the case where the input variables were lesser than the total size or the max size. What if the output sequences have variable lengths? If we know the advance of what length each sequence will have, for example, if we know that will have the same length as input sequence, then we can set the sequence length parameter as we have done just now. Unfortunately, this is not possible in case of predictions, because we don't know how big the predictions are going to be, right? A length of translated sentence is generally different from the length of the input sentence. Therefore, it is hard to figure out what is the length of the output. Therefore, the most common solution is to define a special output called end of sequence token, EOS token. Any output past the EOS should be ignored, and we will discuss it later in the details. Okay, so any output past EOS should be ignored, and essentially what we do is we generate the EOS token as part of our main logic. All right, any questions so far? All right, so till now we have learned how to compute the values using a RNN. But how do we train it? How do we train the RNN that we have just built? We were able to feed the x0, x1, and we get the output. And those outputs were basically random outputs based on the initial random weights that we have, that basic cell must have created inside, right? So if we have to train it, how do we go about it? The answer is very simple. We use the backpropagation. Back in case of training RNNs, we just use the I would not like to commit this script. I'll have to check before committing because there are some changes that I don't want in this script. So Binta, I will see if I need to commit. But I haven't done much changes, right? Or have I? All right. I'll before committing, I'll just check if there is any significant change. All right. So great. Now, for training RNNs, the trick is to unroll it through the time and then simply use regular backpropagation. This strategy is called backpropagation through time. We call it BPTT. So essentially, if you think about the RNN is nothing but the nothing but this kind of a network. We have first one, we fed X, we got Y. Then in the next step, we fed X1, we got Y1, along with we fed the previous step's output, right? So at any step here, this outcome is a function of Y0, Y1, and X2, meaning the outcome at Y2 is a function of X1, X0, and X2. All right. So the way we train in RNN is using the regular backpropagation, and this strategy specifically is called backpropagation through time. Okay. So let's try to understand how RNNs are trained. Just like regular backpropagation, there is a first forward pass through the unrolled network represented by the dashed lines. So here, in the first forward pass, we compute the values, we assume the values of W's and W and B, and we also compute the values of Y0, Y1, Y2, and so on, right? In the forward pass, this is what's going on, right? We're basically computing the values of Y0, Y1, and so on. Now, the output sequence of this network, let's say we are ignoring these outputs, we are only consuming these outputs. The output sequence is evaluated using a cost function called C. C is a function of, say, at 3 timestamps, like a time window of t minimum plus 1 up to t max, where Tmin and Tmax are the first and the last output timestamps steps, not counting the ignored outputs. So imagine that we are only counting a certain window. Then the gradients of the cost functions are propagated backward through the unrolled network. So the gradients of the cost function are propagated backward through the uh, so exactly like usual backpropagation, we are going to find out the values of say y2, y3, y4, or you can say any time window in general. Then we are going to find the cost function or the loss function. We're going to compute that how far are we from actual. This is the cost function. And the cost function, we are going to differentiate. We're going to find the rate of change of cost function with respect to the rate of change of y2, as well as y3, as well as y4. Then we are going to compute the rate of change of y2 with respect to dw, all right? And a rate of change of y2 with respect to say y1, and rate of change of y1 with respect to the x naught, and so on. Y1 with respect to w. All right. So this way we will propagate the error till this point. And finally, the model's parameters are updated using gradients computed using BPTT. Note that the gradients flow backwards through all the inputs used by the cost function, not just the final outputs. So we can't really just consider this as a small network and just compute the backpropagation, right? We could have simply done is rate of change of error, we figure out based on the weight, and then rate of change of y with respect to the. So, all right, let me put it this way. How does backpropagation work? In backpropagation, we essentially compute the impact of W on the cost, right? So rate of change of cost with respect to Y is what we compute. Then we multiply that with the rate of change of Y with respect to W, so that we get the rate of change of C with respect to W. This multiplied by this is what we get. Now, if we just assumed this part, if we just assume this part, we will get the rate of change of cost with respect to W, and we would subtract that from W and move ahead. But rate of change of Y4 is not only a function of W here, it's a function of the previous W as well. It's a function of previous Y3, which is a function of W again, and so on. Therefore, we can't really ignore this because here, when we are writing this function y4 equals W into x4 plus there is a feedback that we're getting wy, there is also another W involved in that computation. Therefore, we can't really ignore this and just compute the rate of change of W with respect to rate of change of cost with respect to W just by this part, right? Because the component that is coming from this side also is a function of W previously. Okay, so we'll have to go till the beginning from here in order to find out the gradients. Okay, so here the cost function is computed using the last three inputs of the network, y2, y3, y4. So the gradients flow through these three values, but not through y0 and y1. Moreover, since the same parameters w and b are used at each time step, backpropagation will do the right thing and sum over all of the steps. Okay, sum over all of the steps. All right, so now let's train an RNN to classify MNIST images. If it's not clear, I can actually go into a little bit more details. All right. So I'll just describe to you again. Okay. All right. Let's just take a look at this one. Right. So imagine that these were the values at every step. So these were the weights, and these were the values S0, S1, S2. So rate of change of error E3 is a function of S3 plus S2, which is a function of S1 and S0, and so on. Therefore, the error has to be propagated backwards. Okay, let me see if I can. Okay. Yeah, I'll just try to describe again and see if I can. Okay. All right. So here y2 is a function of wy into y1, right? Plus x2 into w plus b, right? This is y2, correct? And y3 is equal to, in the similar way, w y into y2 plus x3, this is y3, and so on, right? And y4 equals w of, what is that? W of y into y3 plus x4 into w, usual w and b. So we have these three steps, and there will be, of course, one for y1, somewhere y1 equals y naught into wy plus so and so, correct? Y naught into wy plus, what was that? X1 into w plus b. And here the y naught is going to be w of x plus b, right? And the cost function that you know of, the cost function that we know of is, cost function is, say y2 square plus y3 square plus y4 square, right? This is how it's going to be. This is plus. Okay. So you can see, let's say the cost function is this. Now, what we want to find out is the rate of change of C with respect to W, because we want to find out that value change, correct? So rate of change of, we know the rate of change of C with respect to Y2, right? And we know the rate of change of Y2 with respect to, say, we can differentiate with respect to, say, W. Okay. Here we basically, while we differentiate this, let's say y2 with respect to W, right? It's going to be this. Okay. So y2, when we differentiate with respect to W, it's going to be equal to, this is going to be equal to how much? Rate of change of y1 with respect to W, correct? And wx plus rate of change x2 and so on, right? Now we know rate of change of y2, y1 with respect to w. Now we will again go back and compute how much is rate of change of y1. This is y1, by the way, this is looking bad. So y1 is when we differentiate with respect to w, then this will lead to y1. When we do that, we are going to say y naught rate of change of sorry, rate of change of y naught with respect to w. Okay, let me put it again. So rate of change of y1, this is y1, this is y1, not y2. This is y1, y1 is this. So when we compute y1 by dw, it'll be uh, this dy1 by dw is going to be y naught wy multiplied by, this is again wy, uh, and this one is going to be y naught plus dw plus x1, right? And the similar way, we can keep on back propagating it. So let me put it again. First, we computed dc by dy2, right? And then dy2 by dw, and then dy2 by dw is a function of y1. So we say dy1 by dw2, and so on. So we keep on back propagating it, and y1 is in terms of y naught, so we'll keep on recomputing it. So basically, this is the mechanism that we use in order to propagate the error, right? And right. So essentially, the back propagation here is a bit complex because here back propagation requires the entire previous states and the current states. All right. So while we are computing, since it's an iterative process, it can actually, it is it won't take more than m number of steps if there are sequence size is m, but it's not difficult. It is a bit time consuming for doing it by hand. All right. I hope this is clear why we require the previous steps. Okay. All right. So if we have to compute, or let me just try to see if I can, dc by dw, rate of change of cost with respect to w will be rate of change with respect to y2, right? So here it'll be, let's say it was, say y2 square plus y3 square plus y4, this is square plus this is square plus this is square. So here it'll be 2 of y2. We know the value of y2, so we can feed that. Now, how do you compute? And similarly, 2 of y3 and y3 by dw and so on. So now we have to compute y3, d of y2 and y3, all of these ones. So 2 of y4 into d of y4 by dw, right? We know these three values. Now, how do you compute this part? The way we are going to compute this part is, again, since y2 can be expressed in terms of this, we're going to express it further, and we'll keep on doing that recursively till the beginning. All right. So that's how the backpropagation through time works. Is it clear? All right. So we compute the rate of change of cost with respect to y2, y3, y4. We compute the rate of change of y2 with respect to y3 as well as with respect to the weights, and so on. So we go back in time till the beginning to find out the rate of change of C, the cost function, with respect to W. All right. All right. So let's try to train our RNN to classify MNIST images. Okay. A CNN would be better suited for image classification, but this makes for a simple example that we are already familiar with. So let's look at if we could use this RNN to feed can we use the RNN to for learning the MNIST images. So we treat each image as a sequence of 28 by 28 pixel each. So each sequence X0 is going to be each image. We will use cell of 150 recurrent neurons plus a fully connected layer of 10 neurons, one per class, connected to the output of output of the last step. This will be followed by the softmax and that cross entropy. So this is what is going to happen. So this is our RNN here. This is our RNN, and these are 150. And then there are 10 units here. Okay. And so on. All right. Okay. So is W equals Wx and Wy, because instead of multiplying them Wx with the X1 and Wy with Y1, we concatenate X and Y previous step together, and we concatenate Wx and Wy one top of another. That makes it easier to multiply. Instead of using a for loop, we are just using the matrix multiplication. All right. Now, the construction phase is quite straightforward. It is pretty much the same as MNIST classifier that we built previously, except that an unrolled RNN replaces the hidden layers. Note that the fully connected layers are connected to the states tensor, which contains only the final states of RNN, the 28th output. So you can see here, let me just go back to the notebook. All right, so let's start from here. Okay, so number of steps here, we have 28 here, and total number of inputs are 28. Number of neurons are 150. Number of outputs are 10. All right, so here we are creating the capital X with the size of the this is the M, which is variable, and then number of steps and number of inputs. Okay, so each image is having a size of 28 by 28. So we are feeding the one we are feeding the image in 28 by 28. It has basically total features as 28, and the number of steps, we are basically feeding one row of pixels at a time. We are essentially feeding one row of pixels every time. All right. Then we are defining our basic RNN with 150 neurons. And afterwards, a question from Minda is, can number of steps be not equal to n underscore inputs? All right. It can be if the image is of different size. If our image was of different size, or if we choose to do it differently, let's say we are feeding, say, 5 strips of pixels in a single shot, right? In that case, the number of steps and number of inputs can be different. All right. It's up to us. We can experiment with that as well. So we could say that instead of number steps as 28, we'll make it 14, and we'll feed 4 strips of rows of pixels in a single shot. Okay, those 4 rows will become our dimension. All right. Great. So moving ahead here. So we're creating the dynamic RNN here. We're passing the cell. That's nothing we have already done. Then we are creating a dense layer of how many we are feeding this as the input, states as input, and the number of outputs is equal to 10. So this is the dense layer that we are creating here. Afterwards, we are creating the cross entropy, and then over the cross entropy, we are doing the reduce mean, and afterwards, we are defining an Adam optimizer on top of the loss. On top of the loss, we are going to call the Adam optimizer here. So we are saying optimizer dot minimize, and we're calling the loss. And afterwards, we are just for printing purposes. Here, just for printing purposes, we are going to use this, correct or wrong. All right, just to print the accuracy, we are using that. And then we are reading the data from data/MNIST. Please note that I have created a data folder in the GitHub. So you should check out this. There is in data folder, there are 2 folders. One is fashion and other is MNIST. So MNIST is the one that is containing the data. So we are loading the data here, and we are running this. So the way we are running is for each epoch and for each iteration, as in for each batch, we are feeding here. You can see this is where we are feeding X and Y batch. All right. So the accuracy is actually going good. All right. So this way you can, right. A question from Binta is that what does it mean by reshape this into this form, right? So here the difference is that we are converting the X batch into here we are converting it into sequence and the inputs. Earlier in our MNIST previous examples, we took the whole image, we converted each pixel into the feature vector. Here we are breaking down the batch or the image that we are loading into something such that one pixel is being fed as an input. So, all right, we will continue from here in the next session. Okay, we'll continue from here. We'll understand what's going on here. All right. So -1 essentially makes it like reshape the X batch into 3 dimensions, such that first dimension could be generic or dynamic. Second one is number of steps. Third one is number of inputs. All right. So we'll continue from here. We'll answer this question in the next session. All right. You can see that we have already achieved accuracy of 97%. All right. See you in the next session. Bye bye. Have a good day. So, all right. Thank you, everyone. We'll continue RNN in the next week. We still have around 2.5 sessions left. So we will cover those in the next 2 sessions. Bye bye. Have a good day.